In this lecture, we will discuss homogeneous linear differential equations with constant coefficients. So in this particular example, the equations are homogeneous, and this is talking about second order equations. The equation is homogeneous, so you note that it's equal to 0. We note that it's a second order, and the coefficients, whereas in general they can be functions of x, in this particular example, or this particular case, we have constant coefficients. So we would obviously rearrange the equation so that the coefficient of the second derivative of y is 1, and then we have a constant coefficient for the first derivative and a constant coefficient for the function of y. Now, when we did first order ordinary differential equations with a constant coefficient, the solution was exponential in form. And notice that's because y and its derivative are both in the equation, and the only function that gives us back the same function so that we could actually add together and get 0 is the exponential function. So since we have a second order derivative also and a first order derivative and a function y all added together to get 0, it's a good guess that we might have some combination of exponentials for our solution. So once again, based on the first order result, we could guess that the second order differential equation would also have an exponential, and that it might look something like y is e to the lambda x, where lambda is an unknown. So recall that our approach is, once we guess at a solution or make an intelligent guess at a solution, we take that solution and we plug it into the differential equation to see if it works. So the second bullet point here, the equation listed directly under, is what we get if we plug in e to the lambda x into our second order differential equation with constant coefficients and factor out an e to the lambda x, which of course is going to be common to each term. Now, we don't want e to the lambda x to be 0 because that would be a trivial solution. So what we really want is the coefficients to be 0. So this is our coefficient equation, also known as our characteristic equation. And what we then need to do is solve for the specific lambda that will satisfy this characteristic equation. And then we have a basis set for a solution for the differential equation. So how do we solve the characteristic equation? The easiest thing to do is to use the quadratic formula. And when we use this quadratic formula, substituting in the coefficients, we'll get two possible results of lambda 1 and lambda 2. And this gives us two possible solutions, y1 and y2. So that's going to form our basis set of solutions. Now, in keeping with the theory of superposition, we can then substitute both of those solutions in to find a general solution with constants c1 and c2 that would be determined by initial values, where lambda 1 and lambda 2 were given by the equation on the previous slide. So determining the values of a and b, or depending on the values of a and b, the solution can take three forms. And what we're really interested in is this term that was under the square root sign, a squared minus 4b. So obviously, if a squared minus 4b is greater than 0, we will have two real roots. If a squared minus 4b is equal to 0, we'll have a real double root. And if a squared minus 4b is less than 0, we'll have complex conjugate pair. So three different cases that'll lead to three different functions. So first of all, if we have case 1, we will have two distinct real roots, lambda 1 and lambda 2. And so our solution looks like c1 e to the lambda 1x and c2 e to the lambda 2x. And typically in most physical problems, lambda 1 and lambda 2 are negative in most of the engineering problems we'll encounter. So for example, if you're looking at a damped oscillator in mechanical engineering, if you're looking at an RLC circuit in electrical engineering, we would not expect exponential growth of voltage or exponential growth of movement because this is a homogeneous equation, so there's nothing driving the system. So usually for a physical system, lambda 1 and lambda 2 would be negative, and we would have, it would act like a time constant or some kind of exponential decay factor. So here's an example of an initial value problem where we would have distinct real roots. Here's our differential equation. We're given an initial value condition on y and on y prime. Remember, this is a second order differential equation, so we will actually need initial values of y and its first derivative. So the characteristic equation here is lambda squared plus lambda minus 2. If we now put that into the quadratic formula, we find that we get two real roots for lambda 1 and negative 2. So if we now substitute that in to get our basis solution, we have c1 e to the x and c2 e to the minus 2x. So the next thing that we do is we find the particular solution. We have two boundary values given. We have one on y at 0, which is 4, and we have one on y prime at 0, which is minus 5. So we put in 0 for x into y and its first derivative, generating these two equations, and when we do that, we get two constants. C1 is 1 and C2 is 3. We plug that back into the solution, getting the constants substituted in, and this would be our final solution for y. When you complete this solution, you actually can substitute this back in to make sure it works and gives you both the appropriate initial conditions at y and y prime of 0, as well as provides an identity when you plug this in to solve the differential equation. If we were to plot this, you would find that, that you get a little dip here. So the first exponential term, which is the decay term, dominates initially, and then you get an exponential increase. So the next example is if you have a real double root. So you have lambda is minus a over 2, and that's a double root. So in other words, your term under the radical sign would be 0, and you basically would just use the one solution. Now remember, this is a second order differential equation. So we're going to actually have to have two solutions. And it turns out we use something called the modification rule. In the modification rule, when we have a differential equation that has an exponential solution, then what we do is the first basis function that we choose is the exponential solution, e to the minus lambda x. And the second basis function that we choose is that solution multiplied by x, the first order term. So we have two possibilities then, and when we create our general solution, we will have c1 e to the minus ax over 2 plus c2x e to the minus ax over 2. So, so then this gives us a basis set of functions. The third possibility is if we have a complex conjugate root. If we have a complex conjugate root, you basically get you get minus 1/2 a, and then you get this I times omega, and that can be positive or negative. This is the term that's under the radical in the quadratic formula, and remember there is a plus or minus associated with that. If that term is negative, it's going to generate an imaginary root, and so giving us a complex conjugate pair. And this can be verified by substitution. Now, there's some complex number math and trigonometry that can be done if you substitute this in, and what it turns out is that using Euler's formula and some trig identities that we won't really do in this lecture because you should have been exposed to this in a previous course, what we find is that this first term gives us an exponentially damped term, so we'll get an e to the minus ax over 2. The I omega part is sinusoidal, and since we have complex conjugate pairs, basically that will convert to a sinusoidal term and a cosinusoidal term, each with their respective constants. And the constants obviously are determined once again from the initial values. So the complex conjugate root forms a damped oscillator where e to the minus ax over 2 is the damping term, and the sinusoidal term in the parentheses is the oscillation term. You might remember that if you have a cosine omega x and a sine omega x, basically what that represents really is a sinusoidal function that has had a phase shift. So in electrical engineering, we're very used to it, and we could even